Welcome back everyone. So we have discussed the Moseley's law and also we have seen that how Bohr's atomic model can explain you can say that ad hocly, because there is a ad hoc approximation is there, but still Bohr's law is applicable, able to explain the Moseley's law, Moseley's plot. So it is the beauty, but what is the importance of this Moseley's experiment or Moseley's law, that we have to study. So now we have to study importance of Moseley's work. Why this is so important, right? So first point, what is the first point? First point is, according to Moseley's law, the characteristic X-ray spectrum is actually regarded as the identifying character of an element. Okay, that means K alpha is actually identifying character of the element, right? This is, that's why, because if you change the element, that K alpha peaks change, as I discussed earlier, that K alpha is totally element character depends on the, because if you change the element you will change the Z, and if Z is changed, that the energy of the levels will be changed, and that daily the energy gap, transition energy will also be changed, which actually change the frequency of the emitted photon of X-ray. So that is the case. Okay. Now second point. Okay, before 1913, because we have to keep in mind that Moseley's work was 1913. So before 1913, as I said, this periodic table, in periodic table the elements was actually ordered in terms of atomic weight. But if you order the elements in terms of atomic weight, there is some ambiguity, because we can see that let us say, I do not remember the exact element, but for example, let x, y, z, 3 elements are there, and a, b, c, this if you arranged atomic weight, then if you order this type of other also there, but let us focus on this. So a and x should have the same character, b and y should have the same character, c and z should have the same character, because periodic table claims that the elements in the same column will have the same character. But you can see the y and the c, in some cases this is observed that y and the c has the same character. Okay. So you have to reverse the position of x, y and z, then you obtain a, b, c and x, z, y. But there was no reason behind this. In that time that was not known. Ad hocly you had to do that to make the consistent, that consistent the claim that in elements in the same columns would have the same properties. Okay, this was actually resolved when you actually arrange these elements in terms of atomic number, not atomic weight. Atomic number is important, not atomic weight. So this was actually confirmed due to the Moseley's law, Moseley's experiment. So this is very, very important, atomic weight. Okay, Moseley actually showed that there would not be any exception to arrangements of the periodic table if you arrange the elements according to their increasing atomic number, not the atomic weight. Okay, this was the very, very, very important outcome of the Moseley's work, we can say. Okay, now again in the periodic table there are some vacant places. This element, there should be element, but that element was not known at that time. So there are some vacant element. If you studied the periodic table in chemistry, then you know that in periodic table, when Mendeleev gave the periodic table, lots of elements, not lots of elements, few elements was there which was not that time discovered, but mostly Mendeleev predict the elements at that time, the atomic number, the atomic weight, that elements, that was actually due to this Moseley's law. If you arrange those elements in the atomic number, then you can only observe that. So, the vacant places of the periodic table actually, okay, let me write it. Has been possible to fill. Okay. So, this is another important outcome of the Moseless experiment. There were other outcome as well. Okay. So, but lanthanide element, there are lanthanide element, actinide element, these elements are there, if you know. So, lanthanide elements actually very the nature of those elements are very close actually. So, you can't distinguish where we have to put the elements, because as I discussed, let us say here A, B, C, D, E, F, G, and in the next row there are lanthanides A, B, C, D, E, F, G, like this. Now, you do not know in the same column the nature of the elements should be the same, but all these elements, all lanthanide have the same types of characteristics, same types of same types of physical or the chemical properties. So, it is very difficult to find out the order. So, that is why Moseley's law is important, because Moseley's law suggests that if you should order in terms of atomic number. So, now if you arrange those in terms of atomic number, then it matches, then it is consistent actually with the periodic table. Okay. So, that is also important. Let me write lanthanide elements are more or less identical in nature actually. In respect of chemical and physical also. Properties. So, it was very difficult to identify and place them into the periodic table. So, due to Moseley's law, it was possible to place them in periodic table. Okay. So, this is the very important another result, outcome or consequences we can say of the Moseley's law. And the last one, but this is also very important, the last one is with the help of this Moseley's plot that was given by this linear plot, that root f is proportional, root nu is proportional to the z. So, this plot is also possible. Using this plot we can identify some elements having atomic number more than the uranium, because uranium is radioactive, right, it is very heavy. After uranium, all elements, not after uranium, but after uranium, the elements, the radioactive elements have the very shorter lifetime, that is actually decay very fast. So, identifying those elements is very difficult. So, using this Moseley's law, we can identify that post uranium element, that is another one achievement. So, this was the outcome of the achievements of the Moseley's law. Okay. So, in this part, this is the total X-ray part we covered. We discussed first the X-ray spectrum. In the last class, we first discussed the experimental origin of the X-ray, how Röntgen discovered the X-ray. This was the experimental setup, and after that we discussed the frequency and the wavelength part of the X-ray, and then we also we discussed the soft X-ray and the hard X-ray, that is also important. Then we came into the X-ray spectrum, that is very important. There are two types of X-ray spectrum, continuous and characteristics, and then we discussed the reason behind the continuous X-ray spectrum and the characteristic X-ray spectrum. And using the characteristic X-ray spectrum, we analyzed the Moseley's law, how Moseley gave the law, and how the Bohr atomic theory is able to explain this Moseley's law. Then we discuss the importance of Moseley's work. So, in this part, this atom chapter is actually now you can say the cover, total syllabus is covered, but let me give you the total summary of this total course from the Rutherford model to this X-ray. Then this will be totally completed, and the next 2 classes I think we will discuss the numerical problems. There are lots of numerical problems, so we will discuss that, but let me give you the summary. So, I can erase that. Okay. So, first we discuss about Dalton. We did not write it, but we discussed the Dalton hypothesis or Dalton model, because Dalton gives the atomic the concept of atom. So, after Dalton we started with Dalton, then we goes into Rutherford planetary model given by Rutherford. Okay. What was that planetary model? The same like the Bohr's atomic model, but there was no that discrete energy levels, right? The electrons can roam about nucleus, but there is no specific energy. Any electron can make the circular motion we having the any amount of energy, but there are some drawbacks, we know this. So, to solve this drawback, Bohr's came. So, Bohr's give the Bohr's atomic model, which is very important, and behind this Bohr atomic model there is a postulate, ad hoc postulate, that energy of electrons should be mvr equals to Nh by 2 pi, not energy, the electron should follow this, then only that electron can be stable in that orbit. That orbits are actually allowed, other orbits are not allowed. So, this was given by the considered by the Bohr, and after that we solved other things, right. What we have solved? Using this Bohr's atomic model, we discovered the energy, En, velocity, Vn, Rn, these things we actually discover, we analyze totally numerically, we analyzed. And after Bohr atomic model, okay, we come to the atomic spectra, very important, because atomic spectra was the experimental result. That experimental result should be explained by the theoretical model, and Bohr atomic model was able to explain this atomic spectra. We discussed that there are 2 types of atomic, not 2 types of, there are continuous spectra and discrete spectra, or we can say line spectra, band spectra. This type of spectra was there. Also in other way there are emission and absorption spectra, This atomic spectra was there, that was we also discussed this continuous atomic spectra, and then we discussed how Bohr atomic theory was able to explain, but there was some also the flaws. So, after discussing this atomic theory, we discussed the success also, yes, and failure of Bohr's atomic model. Okay, this was also discussed. After that, we discussed what we have discussed also. With this, we also discussed the ionization energy and potential. What does it mean, ionization energy and potential? That was also discussed, and at last we came into the X-rays part. This X-ray part was then we discussed the X-ray spectrum, and also we discussed about the soft X-ray, hard X-ray. This is also important. After discussing X-ray spectrum, there are 2 types of spectrum, continuous and characteristics, and then we came into the Moseley's law. So, this was a total picture. We start with the Dalton model and we end up with the Moseley's law. Okay, this was total our chapter total summary, you can say, not summary, just we draw the our path, total the course path of the course, how it runs. Okay, but at the last we will in the next, from the next class we will discuss the numerical problems, and while discussing the numerical problems also we will solve the, we will also revise our theoretical background as well, because that is also important. But before that we have to remind the formulas. Formulas are important, so that we will remind today, and then from next day we will discuss the numerical problems. Okay. So, first H nu is equal to E final minus E initial. Okay. Next, this is very important, C is equal to nu lambda for any electromagnetic radiation, this is important. Next, for Bohr atomic orbit, nth orbit, Rn was epsilon naught n square h square divided by pi m z square, this is Rn. Ln was equals to Lh by 2 pi angular momentum. En energy should be equals to minus 1 by 4 pi epsilon naught z square by 2 Rn. Okay. Then we have to mind it that what was the Bohr radius, first Bohr radius, that was epsilon naught h square divided by pi m square. For hydrogen atom it is actually not, for hydrogen atom it is actually 0.53 Armstrong, and also we can write that E n is equal to minus R C h by n square, where R is the Rydberg constant and R is actually m e to the power 4 8 epsilon naught C h cube. This is for hydrogen atom. The value is actually 1.09737 into 10 to the power minus 7 meter inverse. Ground state energy of hydrogen atom is actually E1 for ground hydrogen atom only 13.6 electron volt. This is also discussed, and the formula, that Rydberg formula, that was this is the Rydberg formula. Lambda is the corresponding wavelength, R is the Rydberg constant, and the series, what was the series? Lyman or Lehman, for Lehman it was actually 1 and coming from 2, 3, 4 so on. Lehman, Balmer, it is 2, 3, 4, 5 so on. Then Paschen or Passion actually 4, 5. Okay. Then bracket and Fun. This was the series of. Okay. Atomic spectrum, so on. Okay. Now for the, this is done, and next is the, okay, for X-ray the lambda minimum was actually Hc by k naught, and k naught we can write it as Ev, because energy of electrons would be E times V, which is the potential difference, and okay, this is the lambda mean, that is it. Okay, we can write it. So, this was the total, and also the and the last, the mostly, that I forgot, the del nu should be proportional to Z. So, this is our total formulas, required formula we have discussed totally in this throughout this course. So, let me stop it, let me stop here. So, we have to cover the whole syllabus of this atom, and from the next class we will discuss the numerical problem which based on these basic formulas, and also simultaneously revise the theoretical background as well. Okay. So, thank you, let meet again in the next class.